Hi everyone, I'm Catherine Volle, Assistant Professor of Biochemistry. Today I'm going to speak with you about developing scientific knowledge. Most of you have probably learned about the scientific method. It's often presented something like this, usually starting with an observation, then moving through discrete steps until you reach a conclusion. This description of the scientific method is driven by hypothesis building. Simply put, a hypothesis is an explanation of what you observed. For example, if you observe that the light suddenly went out, you might hypothesize that the light bulb burnt out, or you might hypothesize that the power in the building was disrupted. Then you could go about testing your hypothesis and hopefully reach a conclusion as to why the lights went out. Unfortunately, this description of the scientific method doesn't really fit well with how scientists actually do science. Personally, I don't like to focus on hypothesis building as I design my research, and instead focus on asking questions. One problem with hypothesis building is that it's limited to the hypotheses that you can come up with. Focusing on a question, like why did the lights go out, lets you think more broadly than I think the bulbs burnt out. Furthermore, asking a question doesn't bias my interpretation of the data I generate. People like to be right, so sometimes there's an assumption that if the data don't conform to your hypothesis, then there's something wrong with the data, which usually isn't true. My mentor's mentor used to say, the data are what they are, and it's up to the scientist to figure out what it means. Finally, I prefer to focus on asking questions because it works better with how I actually do science. Science is complicated, and figures like this are a huge oversimplification of what scientists actually do. They make it seem like there's an orderly set of steps to follow, and in the end, you'll get a nice, neat answer. The idea that there's some orderly set of steps to follow describes an algorithm, not how we do science. There are many different aspects of science, some of which don't even show up in the algorithmic version of the scientific method. Things like investigating the known and communicating with others. These are key parts of the scientific process. You don't want to just repeat what others have done before, so checking to see if an experiment has already been done is a key step in defining research. And scientists often bounce around between the many different facets of science, from observing to defining the problem, to communicating with others, back to defining the problem, on to carrying out the study, and so on. If we set the question as our focus rather than the hypothesis, it makes this bouncing around easier to keep track of, because you always keep coming back to that core question. I like to think of science using this problem-solving model from Jeff Conklin. Many people think about problem solving in a linear, algorithmic manner, just like the scientific method. But in the real world, problem solving is much more complicated. In this model, you keep returning to the problem in order to solve it. And each time you return to the problem, you refine it a little bit more. If we think about doing science as problem solving, as we generate data, we continually jump back to the problem/question as we try to get to the solution/answer. But now we've reached the limit of antibiotic that we can use, so we need a new strategy. These bacteria have a protective coating. What would happen if we removed it? On the first try, Helen removed the protective coating, but all the bacteria died, even before she added the antibiotic. Brute force isn't going to work, so she's more gentle the next time, and the bacteria survive their coat removal. Now we can go back to adding the antibiotic and finally kill the bacteria. But it's no good if an experiment only works once, so she repeats the experiment again. Now we have a new question/problem. What is the protective coat actually doing to protect these bacteria? Now we're back at the beginning. Working through Helen's problem, we see that scientists fail a lot. It could be small failures, like having trouble getting an experiment to work. I spent a full year trying to get this one experiment to work. That's a lot of failure. Blood, sweat, and tears went into troubleshooting this experiment. But every time I ran this experiment, I learned a little bit more. One experiment is like very complicated clockwork, and every single piece needs to work together. Just like it would take time to assemble a working clock from individual pieces, it can take a long time to get experiments working. Scientists can also make major errors, like sending out contaminated testing kits. When the CDC first released COVID testing kits, the mock samples were contaminated, and lines showed up where there shouldn't be lines, casting doubt on the accuracy of the test. But as long as scientists learn from our failures, it's usually okay. It's also why scientists work together and share data with others. We rely on others to test the data, add new data, or simply bring a new perspective and see something the scientists originally missed. This brings me to scientific humility. Because SARS-CoV-2 has disrupted every aspect of our lives, the general public are anxious for new information, and scientists are rushing to provide it, showing how science works in real time. It can seem like scientists don't know what we're doing. But scientists are doing good science, which means they're drawing conclusions based upon the data available at the time. There's always new data coming, and sometimes it's better data, which means we may need to change our conclusions. An example of this is face coverings. Initially, face coverings weren't recommended based on the data available in March, but now it's September, and we have a lot more data that says face coverings are crucial for stopping the spread of the virus. But scientists are people, and people can be messy. In general, people want to be right, and it can be hard to admit when you're wrong. But not admitting when you're wrong and holding on to ideas that aren't supported by data can be dangerous. Such is the case of Peter Duesberg, a professor at UC Berkeley who refuses to accept that HIV causes AIDS, despite overwhelming evidence that it does. He believes that HIV treatments and recreational drug use cause AIDS, and his advice to someone with HIV would be not to treat it. It can be hard for the general public to know what's good science and what isn't. So scientific literacy, or the ability to engage with scientific issues in a logical manner, is really important. So what can you do? First, you could become an expert, dedicating your career to whichever flavor of science interests you the most. That takes a long time, and even then there will still be scientific issues on which you are not an expert. So next, prioritize experts. These are people who have significant experience in a specific field. Create a hierarchy of expertise. So if you want information about infectious diseases, go with Dr. Fauci, who has dedicated his career to the study of infectious diseases, rather than maybe a doctor who specializes in family medicine. Even then, you should prioritize the doctor who specializes in family medicine over a random blog post you found online. You can also try to find the data for yourself, though this is often difficult for the general public. Scientists usually don't share their data in a way that's easily accessible, so also remember that you might be reading someone else's analysis of the data. You can look for conflicts of interest, where someone associated with the research might directly benefit from the outcome. It doesn't mean that the data are necessarily bad or not to be trusted. But if a scientist from the Mars Corporation, who make chocolate candy bars, are telling you that chocolate is good for your health, you might want to be a bit more skeptical. Finally, you can understand how science works, and remember that new data are being generated all the time. If experts are changing their opinion based on new data, science is working the way it's supposed to.